Is, if possible, not to have to study from the book for tests, just study from the notes. Since we want to study from the notes, we got to make sure the notes are complete as possible and not missing anything. So the reason I wanted to do this is just to take a look, and see if there's things that we can add to it or whatnot. And so let's take a look at the, this is from day one, so this is going back, Lavoisier in the beginning of chemistry, science that studies how molecules behave, composition, structure, properties, and reactions of a substance. And so I see chemistry A, B, but is there a take-home point? This is normally what I'd write in the annotation here. So what's the point of A and B, or are they equally as important, or is it self-explanatory? Because when I look at this, A is correct, and then B is correct. But I have a little note here. So is there significance to A and B? Uh-huh.
I put it like that because they're both equally correct, but the B is what you, like the preferred definition, and I didn't mark that, but...
Okay. Yeah. Actually, A is what was on the PowerPoint, but A was too narrow of a definition because scientists don't just study molecules. So the point was that, and this is what you could do later on, because later on we got additional information, so you can always go back and add or annotate. And so I do heavy annotation trying to make connections here. Connections were, not only do we see molecules, but what else do we see in nature? Well, I mean, as far as what are molecules? Molecules are elements combined into a unique structural unit, and that structural unit can't be further broken down without it losing its identity, like water. So it's the smallest unit. And it was just called smallest unit, but it's the smallest structural unit of water. And then I contrasted that later with what? See, these are the, well, it depends. If you've been flipping through your notes, then you would see, okay, here I see there's molecules, and there's this, and then there's this. And then you make the connection back here, and then that's where you start annotating the notes. You start annotating the notes because we go back, and this is like, something you learned a while back ago, but now, there's additional information you can go back and add to that. This is actually in science. In science is, you don't discover the wheel, you build up on other people's work. And so this is a progressive build-up. And so you go back and look at what other people's work, and then you put it into a modern context kind of thing. And so we could do the same thing here, and so molecules, and so I'd write a little note here, that's too narrow because not only do we see molecules, but what else do we see? And this is something that should be automatic if, you've seen it enough times. If you've seen it enough times, then it becomes automatic, It's just, all it is repetition. But the thing is how do you get repetition if I only say it once? So does somebody have that recall? And so this is, again, I can't emphasize how important this is because this made a huge difference in me and my I'm not saying it's going to make a huge difference in your studying, but after I did this, then life became much easier, much easier. Otherwise, it was like, yeah, not quite ready. So you just build up on it. Well, anyway, the other structures are that we see could exist as atoms, like helium. Could exist as ionic lattices or covalent lattices. So this is where, when we talked about it later on, you can go back here and just say, okay, it's too narrow because not everything occurs as molecules structurally. Things occur as atoms, like helium doesn't form molecules. Argon doesn't form molecules. Neon doesn't form molecules. Diamond, does diamond form molecules? No. What does diamond form? what I call the covalent. I call it covalent lattice and ionic lattice, but I didn't explain what they were. I just told you. We'll talk about those later. But when we talk about those later, then you go back and you make that little connection, you know. And so the important thing is to be able to make these connections across the material. Now, if you can't, you know, this is too much. It isn't really. Anybody can do this. You know, it's just you got to see it more and more times. You know, eventually, when you see it enough times, it becomes routine. Well, let's go on here. So that's the take on the molecule, smallest unit particle of a pure substance that can exist independently and possess the identity of the substance is good. Chemists ponder on things that make up the universe, such as molecules. Good. Lavoisier, father of modern chemistry, author of this. Okay, these details, like for example, what the title of the book or when it was published, I'm not going to test you on. When did he publish it? You know? And so those types of things, we don't have to worry about memorizing. Okay. But you know, as you know, it's like in the 1700s. Conducted experiments and formulated theories, revolutionized thinking that was accepted from the time of the Greeks. Okay, that's good, but you know what you want to do is you want to kind of summarize this because, like, what was before Lavoisier? Well, actually, you know, what was it before? You know, why is he thought as the father of modern chemistry? Before was more of alchemy, right? And so we had a little talk about alchemy here. So you could just write like before it was alchemy, and it wasn't really, you know, this is more what versus the alchemists. Well, alchemists probably did this as well, but the alchemists had the goal of the elixir of life, and the converting lead into gold. But what was the difference between Lavoisier and the alchemist? And so you put this in. The connection here is this: Lavoisier and the scientific method. These two are connected. So this is where it comes in. So you'd have a little arrow or something, scientific method, or the point. And so the beginning of experimental chemistry and scientific method. So, okay, the experimental chemistry, that's good. Scientific method. Observation. These are the steps of scientific method: observation, patterns, trends, law, empirical equation. Laws are unbroken mostly. Yeah, rules can be broken. Good. Hypothesis. It's tentative fundamental explanation. Good. Theory, accepted fundamental explanation, needs to predict, describe. Law, make new unforeseen observations. Good. That's all good. Features of the scientific method, same as step E. Experiment, I guess, be skeptical. Okay, but as far as what I would have done here, as for additional work would be, I would provide an example of the scientific method here. The example. What was the example? You probably should be able to think of at least two that I talked about in class or more. Phosphorus, yeah, the Lavoisier, yeah, he burned both phosphorus and mercury, but that was just the start of the experimental, and then but Lavoisier didn't come up with a theory that explained that, but that was the beginning. So let's say the beginning of experimental chemistry, where you take that and then look for patterns, and the pattern in nature was that phosphorus and mercury One burn, mass didn't change. And so we could put that in here, you know, a little pattern. And then where did that pattern lead? To what law? Which law? Conservation of mass. And conservation of mass led to what hypothesis? I'm sorry? No, that's not a hypothesis. Laws are not hypotheses. A law is just some kind of mathematical pattern. That's it. All a law is just a pattern that keeps repeating itself that doesn't seem to be violated. That's what a law is. But a law doesn't really explain where that pattern came from, or you know, the origin of that pattern at the fundamental level. And so that law, the law of conservation of mass, led to what hypotheses? You see, this is not good. This is not good because it should be, you know, it was discussed almost 2 weeks ago. If it was discussed almost 2 weeks ago, you should have seen it at least 10 plus times, you know, and at least read it. Like, if you read something 10 times, then it's, you know, pretty soon you'll have it memorized, for sure. And if you haven't memorized, it should come out much quicker. This example you should have seen, because I repeated it like 2 times or 3 times, right? And it should be quick. And so I'll tell you, you know, it's probably the same, similar, because I didn't really do this when I was. And I still, you know, managed to do okay, because when I was at Santa Barbara City, I was, you know, it wasn't that. I devoted a lot of time to study. You know, I was consistently on the dean's list, and so when I went to UCLA, I didn't. It took some time to get back on the dean's list, and the way to get back on the dean's list is to. Well, I couldn't do the same thing I was doing before, and so these are the things you want to do. And so I would do some more annotation in here, and then give an example, you know, or. You know, or add some, you know, this is my opinion of this, or this is my thinking of this. And so, you know, there'd be a little bit more, like here, like a take home. If I'm going to remember one thing, what do I need to remember? You know, because if you think about exams are going to be, you know, what's the most important stuff. And so normally what I do here, when I go through my notes, is I write down, you know, the most important take home point, you know, of this section, or of the chapter. What are the key take home points of the chapter, you know? And those are the things I concentrate on studying, because, you know, a good chance is that you're going to be tested on the most important, and not really the obscure stuff, you know, as much. Sometimes you'll be hit with obscure stuff just to see, you know, your depth of knowledge, you know. And so, for sure, I would have had a definite example. I gave multiple examples. One was the apple falling from the tree, which led to the theory of gravity. The other was the Lavoisier's experiments leading to atomic theory, which was proposed by Dalton. And we talked a lot about atomic theory, because what proof did he have for atomic theory? You know, and so those should be automatic. Well, you know, because here we make the connection, even though I didn't discuss it on this day. You know, you make the connection back here, and it should come. And so if you do that, you'll find yourself, you know, the classes will become much easier, and your academic life will become much easier. And, you know, you don't have to have a fantastic, my memory's bad. You don't have to have a fantastic memory. You know, if you see something enough times, it's like, you know, the stuff you learned in kindergarten, you've seen it so many times by now, you don't want to go back to kindergarten and study, do you? You know, it'd be a waste of time, you know? And it's not because you have a fabulous memory, it's because you've seen it so many times over and over again. And so this is the same thing with this stuff. You know, you see it over and over again, you just remember these things. Well, the problem is that, well, you know, when I was at UCLA, I was trying to figure out how to change my study. So I ended up reading a number of books on studying. Professors even gave out handouts. When I took biochemistry, the professor gave each student a 25-page handout, how to study biochemistry. Now I remember quite well because I tried everything in the handout. One was to isolate yourself in a noise-free room. And so there's a library at UCLA, Powell Library. You can go way down in the basement there, and it's very quiet. But it's very quiet, but sometimes little noises will pop up, you know, and so it's so quiet, those little noises become extremely distracting. So I gave up on that. I ended up studying more at Kirchhoff coffee shop because it was so noisy. There was white noise, so it's a lot easier to concentrate. But anyway, he had so many tips. The other tip was read the chapter 5 times. I didn't have time to read the chapter 5 times. There's no way I could read the chapter 5 times, because I'm a slow reader, and you must be a speed reader because, and so I had to devise other, just like you know, you'll have to figure out what works for you. I'm just telling you what worked for me. If it doesn't work for you, then you should start looking for it. It depends if you're doing fine and you remember this stuff, but it sounds like if you can't recall this stuff, it's not doing fine. I'll tell you, because you should be able to recall a lot faster, especially on time tests. If you take like let's say the GRE or something like that, wow, you're going to be in for a shock because you're going to have so many unanswered questions if you can't do it fast. You know? Same thing. And so try to get that recall by just going through this stuff, and then it'll pay off in the end for sure. All right, so we have the classifications of chemistry. There's so many sub-classifications that, you know, this is kind of just general. You don't need to focus on that, but it's good. Analytical, bio, organic, inorganic, physical. This is okay, then learning Chem, you know. Number 1, commit sufficient time outside of class. That's good. And people have a whole bunch of different ideas about what's sufficient time. You know, I should plot it out. And I was going to make a plot of how much time people have to study chemistry. It varies all over, from minimal to a lot. And so make time, thinking like a chemist. This is good. Chemists always think properties, composition, and structure. You know, because if you want to know how things work, yeah, the properties, composition, and structure. That's good. Use observation theory for detail. Patterns. Okay, so but there should be something a little bit more here probably. What should we add to that? Yeah. What should we add to that? And it was probably difficult at this time for it to register. But I talked about there's 2 types of, like physics. There are 2 types of physicists. If you look at the Hadron Collider, there's the theoreticians and then there are the experimental physicists. Have you heard about this kind of stuff? Now, theoreticians are just in the computer and simulating things. The experimental physicists are just doing the experiment. Well, the same thing happens in chemistry. You have your theoreticians and you have your experimental. But the best is, well, we're not going to be put into one camp. So, for example, drug design. If you're doing drug design, a theoretician will pick, based on the computer, pick the best, what they think will work the best for a specific target. But then the experimental people will synthesize a whole bunch of different formulations. I didn't use drug design. Does anybody remember the example I used? The example I used, I know it's probably 2 weeks ago, so it's long gone, but the example I used was a catalytic converter in a car. Platinum is very expensive. And so you have your theoreticians who are trying to look for a good substitute for platinum, and then you have your experimental. The experimental people will synthesize a whole bunch of different formulations of it and then try it out and then see. The same thing happened with the blue LED. which I think I mentioned in passing. The blue LED was like the holy grail of LEDs. The red LED was found, the green LED was found. It was just, if you have red, green, and blue, you can make the whole rainbow of colors, right? And so, did I mention who got there first? Was it the theoreticians or was it the experimental? It was the experimental, right? The experimental. The experimental got there first. And so the point of this is this. The whole point of the whole discussion I had earlier in terms of chemistry is because of the push. I know in schools now there's a huge push away from memorizing anything because a lot of, and I hear this a lot of people say memorizing is not learning. Memorizing is not learning. It's a waste of time, and so I think, wow, that's a big mistake, because that's all experimental. Experimental chemistry is like memorizing things. You memorize your experimental observations, or you write them down so you don't have to memorize them, but essentially you kind of memorize them so you can catalog that and find the patterns. And so that wipes out. And so they're approaching education from a purely theoretical point of view, but the theoreticians aren't always successful because the theoretical means, one, you have to understand the theory very well. And if you look at the theory of atoms and atomic structure, the math is horrendously difficult. The math is so difficult that people use like guesstimation to figure out the answers. The guesstimations are called approximations, and so they're guessing at the answers there. And then the answers that they come up with are off a little, and can be off quite a bit. And so the theory is not easy. And if we could just use the theory, then we don't have to memorize everything, because theory should be able to predict everything, basically. And so the point here that I was talking about was the two-pronged approach. We're going to approach things from both. Of course, we want to know as much theory. So this is what I was talking about, theory. And we want to know as much observation as possible. And so we got to memorize certain observations, So the example is water a liquid, gas, or solid at room temperature? And somebody who doesn't like memorization will go, well, I don't know. I'll just look it up, or I'll just calculate it based on theory. Okay, you calculate and prove to me that water is a liquid at room temperature using theory. What's easier, just memorizing water is a liquid, or proving that it's a liquid at? And when you prove something, you're going to be challenged on it. You can't just say, well, I saw it because, well, that's observation. That would be memorization, right? And so what's easier? Well, chemists are going to do the easiest thing. Chemists, they don't want to do extra work, but there's certain minimum stuff that you have to memorize. Otherwise, you can't do chemistry, basically. And so that was the point of this. We use both observation and theory to understand chemistry in terms of properties, composition, structure. And then, or we use patterns. We don't need to know the theory to predict, but the observations should lead to some kind of pattern in which we can make predictions. And then I showed this horrendous chart. Do you remember that horrendous chart I showed on the board with all that stuff? And you go and you look at that. Wow, do you want to memorize that? No. And so the point of that chart was to look for patterns in that chart and not memorize it. People have asked me, not in Chem 4, but in Chem 1B, people have asked me, do I need to memorize this chart? That was a horrendous chart to memorize because of a lot of entries and a lot of stuff in there. And I said, no, but of course you don't need to memorize a chart, because like a flashcard, but you need to look for patterns and memorize the patterns. That you have to do. And so that was the whole point of this, And so all the additional details might be long, but that's there's only so much you can write down, And so this is why, like, right after class, you know, I might remember, oh yeah, there are examples of this or other stuff. So right after class, I might add those down as annotations, as long as I remember. And I had to do this. This is why I reserved free time right after class. Free time right after class is because I could remember things, but I couldn't write it down at the time. And so right after class, I'd write down everything I remembered, but it was too slow to write down. And then I would have as complete of notes as possible. But the other thing I'd do is I'd compare. You know, I'd compare with the other students to see, you know, if I missed anything or whatnot. At UCLA, they have something called a note-taking service where you pay a professional note-taker to get a copy of their notes. That professional note-taker goes to the professor and makes sure with the professor that he didn't or she didn't miss anything presented in the lecture, so the notes were complete. And so I always bought those if they were available, but they're only available for the lower level classes. They aren't available for the higher level classes, of course, you know, because of the economics of the situation. So, you know, eventually you have to learn to take your own notes and have them complete, because of the higher level classes, that's where you really need them. But anyway, going back to this, I would do that, but the thing I hated is if I had a class. If I had a class right after the other class, then I know I lost memory, and I know I forgot things, and so I knew my notes weren't as complete, so I had to make extra effort to make sure that they were complete. If something happened and I couldn't do it until the next day, then, you know, it's easy to tell. I didn't need a psychologist telling me, or a neurologist or whatever telling me I lost a lot of the memory. I just forgot a bunch of stuff. And so stuff like 2 weeks ago is like long gone, you know. And so this is why it's critical. And so this is why I wanted to talk about the notes. I want a review of what we talked about, you know. Let me just see. Like yesterday, you know, yesterday I asked you, let's flip to the back of this. Yesterday I asked you what we talked about. And so what I was hoping was that, let's see, where were we? You know, when we were talking about what was discussed the day before, yesterday, you know, I wanted this, and I see, I wanted somebody to tell me about energy. You know, total energy, you know, potential energy, kinetic energy, and give me specific examples of that, you know. But what I got was, you know, I just got some general endothermic, exothermic, but, you know, maybe you had it in detail, maybe you didn't. But I just didn't push it any farther. But this is why I want to see what people had in their notes. But, you know, can you give me an example of total energy? You know, is total energy, we talked about total energy is conserved, you know. The energy before is equal to the energy after. And so therefore, whenever we're looking at any kind of change, whether it's a physical change or chemical change, we have to consider both the change in potential energy and the change in kinetic energy. And so yesterday I was hoping that that would be brought up in more detail with some specific examples of this. Specific examples like this. You know, but the thing is though, when I look, and I know some stuff is missing here perhaps, but when I look, I'm looking for a special way it was written, you know. And if that special way that's written doesn't quite make sense, then we should talk about it. And the special way it's written is like this, you know. Where, you know, on the y-axis there should be an arrow, you know, showing that we're looking at relative energy. And so just energy increases as we go up this way. And then, I don't know, but convention, I just wrote it by convention. Convention is we write a line here indicating that this is at this energy, and we write a line here indicating this is this energy. So we want these underlined here. That's just because it's always written like that in this diagram, which I didn't label at the time. This type of diagram is very common in chemistry. It's called a energy level diagram. We're going to see more of those energy level diagrams. So this is the first peek at energy level diagram. Well, anyway, there are other little things here. This is good. Higher chemical potential energy, more reactive. Lower chemical potential energy. Less reactive, more stable. This is very good. These are the take-home points you want. But this is just potential energy. What about the kinetic energy? Oh, what's up here? You have the kinetic energy. Same kinetic energy because same temperature. Good. And so we have that. Higher potential due to dangerous methane. Well, it's dangerous methane and oxygen. We have to have two to react here. You need the fuel, which is methane, and you need the oxidizer, which is oxygen in this case. And so I call it a dangerous mixture. If it's methane alone with no oxygen or no oxidizer, then it's fairly stable. It's not going to react with anything as long as there's no oxygen around. Compared to this mixture, this is a much more stable mixture. So this is good. And I don't know if I said anything about, since the energy is conserved here, the energy has to go somewhere. If we lose energy here, where did that energy go to? I used a word for it. The reason I use the word for it is just so that I called it something, and it's actually the name that goes. I should have written it down. Actually, it goes into the surroundings. So any of this, the excess energy here, that is, if we lose energy, it doesn't disappear. The lost energy goes somewhere because energy is not created. It doesn't magically appear, and it's not destroyed. It doesn't magically disappear. The energy goes somewhere. And where did the energy go? Does anybody write it down? Starts with an S. Surroundings. Good. It goes into the surroundings. And, when we get to thermo, we call this the system, and then the system and the surrounding exchange energy back and forth, since energy can't be created nor destroyed. And so it's not critical that you know it, but it's kind of nice if you had it there, because then it would just drill it down so that by the time you get to thermo, it's automatic, surroundings. And you've seen it a bunch of times, even though it's not in our book, The problem is this. The reason why I might jump ahead a little bit is because of the repetition, because you have more time to let it, set into your memory. And so there's certain vocabulary and certain concepts that I'll cover a little bit earlier, just for that. But otherwise, we jump into it and you're tested right away. Okay, good. And so those are just some comments on the notes. Of course, if you want to, this is what's good about this. Like the note takers, the professional note takers always consulted with the professor. And you're welcome to. We can go through your notes and make sure you're not missing anything. After class, in class, whenever. I'm happy to review your notes with you. I know it's hard to get everything down, or you compare with your friends. If your friends, and just make sure. That way, you don't ever have to open the book. If you don't have to open the book for the test, that's good. You'll want to review the homework, of course. The homework and your notes. Because reading the notes is quick. So we'll just do a little bit right now, and then we'll continue. But thanks. No, it's good. I mean, the notes are good. A lot of people don't take notes. I've seen it, but not in high-level classes. In high-level classes, there's nobody not taking notes, unless it's a talk and they aren't really worried about it. When you get to higher and higher level, people are taking notes. is too much information to remember. You know. Maybe for lower level classes it's okay. You know, it depends. If you find the material easy, then you don't necessarily have to, you know. But I want to talk about just one topic before we start the lab, and that is percent, ppm, ppb, ppt. All these are the same thing, basically. They're just describing the composition, or usually composition. We have different percentages. And so the different percentages are this. Water. What percent of water is hydrogen? And so if I do H2O, then what I can do is I can do something called an atom percent. And later on we'll also know this is a mole percent, but we haven't talked about moles yet. But if you know what a mole is, an atom or mole percent is fine. And so when I look at it, there are 3 atoms total. Right? And so if I have 3 atoms total, and I'm looking at atom percentage, then it's 2/3. 2/3 hydrogen atoms. That's what it is. And so how do I convert a fraction into a percentage? How do I convert a fraction into a percentage? So it's 2/3 hydrogen atoms. To convert a fraction into a percentage, I multiply it by 100%. If I multiply by 100%, then it's going to come out to 66, or I'll just do it 67%. Keep it simple. 67% hydrogen. Well, 67% is just equal to 67 hydrogen atoms. It's rounded. This is round off error. 67 hydrogen atoms for every 100 atoms, total atoms. I'm sorry if it's hard to read. And so this just says 67 hydrogen atoms for 100 total atoms. And that's the same thing. 2 out of 3. This is 2 out of 3, right? So that's to convert it into a percent. That was the first one. What if I want to do it by ppm? ppm by atom. If I want to do a ppm by atom, sorry, this table's not so good. Rather than multiplying it by 100%, do you know what I do? I multiply it by 1 million ppm. And so this this just means this. I'll just punch it in my calculator, right? Punch it in my calculator, and I'm going to get, well, actually, what will I get? I should know. Well, I'll just do it in my head. This is what I'm going to get. I'm going to get, what would it be? It's going to be a huge number, isn't it? 0.67. Well, let me just do it. 2 times a million divided by 3. I'll just do it this way. 670,000. I'll just round it. ppm. Hydrogen. Well, 670,000 ppm hydrogen just means this. I'm going to have 670,000 H atoms. I'll abbreviate H as H for hydrogen, out of 1 million total atoms. So if I had 100 total atoms, 67 would be hydrogen. If I had 1 million total atoms, well, 670,000 will be hydrogen. And so these two are the same. 67% and 670,000 ppm are the same number. Do you see that? It's the same number. How about parts per billion? Well, for parts per billion, I instead of multiplying it by, this is percentage. Rather than multiplying by 100%, rather than multiplying it by a million ppm, we multiply by a billion. So we take the fraction and multiply by a billion, ppb. And so this is going to give me 670 million ppb. In other words, 670 million ppb is 670 million hydrogen atoms for every billion total atoms. Parts per trillion, what do you think? Can you guess what we do there? Multiply by a trillion ppt. That's it. But what we use depends on the convenience, We'd like to use numbers between 0 and 100, but if we start using thousands, 10,000, million, it becomes inconvenient, right? And so in this case, out of all these, which one is the easiest to express the composition of water based on atom percentage, or based on composition, atom composition, percentage. These ones become inconvenient. These are hassle. However, there are other things that have very low concentration or very low percentages. And so when we're looking at that, then it becomes more convenient to use other units. And so another example would be, let's say I had a swimming pool, and then this pool had 0.0001 gram of chlorine for every 1 gram of cool water. And so what is this equal to? Well, in terms of percentage, what would this be equal to? Well, in terms of percentage, what would you do? You take this fraction and multiply by 100. And so in terms of percentage, it would be 0.01% chlorine in the pool water. In other words, 0.01% just means I have 0.01 grams of chlorine for every 100 grams of cool water. Well, 0.01%, that's a little less convenient, maybe, then. Let's go with, let's try something else rather than percentage. Let's try parts per million. If we did parts per million, what will we do? We take this fraction and multiply by 1 million. So that's multiplying by a million means moving it 6 places over. 1, 2, 3, 4, 5, 6. And so this would be 100 ppm chlorine in the pool, because we're taking that and multiplying it by a million, right? And so 100 ppm, and that just means that I have 100 grams of chlorine for every 1 million grams of pool. You see that? If I did the same exact in parts per trillion, then it would be 100,000. This would be 100,000 parts per trillion. Well, out of all these, which one do you think is most convenient? Percentage, parts per million, or parts per trillion? Well, oftentimes we don't like these small numbers, 0.01. It's kind of a hassle. It's just a matter of convenience. And so maybe this is easier, 100 ppm. It's easier to say than 0.01%, although they're exactly the same number. Do you guys see they're exactly the same number? And so this is why there's a disconnect. You guys already know how to do percentages. If you already know how to do percentages, then that means you already know how to do parts per million, and you already know how to do parts per billion, parts per trillion, because it's exactly the same thing. Exactly the same thing as percentages. I could say that, but you know, it does take some getting used to. Just spend a little bit of time getting used to it, because there are going to be people who absolutely don't get it and refuse to get it. Every semester, they don't see the connection, and so that just means just looking it over, and then eventually it clicks. You know, and once it clicks, it's because it's so easy. But until it clicks, it's, you know, you're banging your head against the wall or doing something to make it, you know, click, but it's not clicking. And so sometimes the problems are exactly the same way. You know, problems seem so challenging looking at it, but you know, the process of repeatedly looking at that problem, you know, eventually it just clicks, because I think your subconscious is working at the same time for challenging problems. All right, so you know, these are conversion factors. Conversion factor. You know, we use these conversion factors for dimensional analysis calculations. So we've got to be able to derive the conversion factors from these types of problems. All right, so I just wanted to talk about that, and then we're going to look at some of the challenging dimensional analysis problems a little later. But I had